So today's speaker, Christina Yeo, Korean Yeosujin, right? So from UCLA, the PhD student, supervisor Michael Black. She is going to talk about Janus correlator. 네. Yes.
Yeah. Thanks for the nice invitation. It's nice to finally set foot on the campus after just kind of walking around for so many times. As the instructor said, I'll be talking about 2-point correlators in Janus spacetime. I'll go into what that means and the equation of motion that we get from that setup, which is called Heun's equation. It's based on a recent work with my advisor, Michael Gupro. It's the archive number. Yeah, so I'll first go over what the Janus solution is. I'm going to look at the simplest construction of the Janus solution, and then I'll also explain what Heun's equation is and how we get the connection coefficients, which is the data we'll need to calculate the 2-point correlators explicitly. And I'll tell you how we can read off the spectrum of the defect operators and the OPE coefficients using the expected form of these quantities. And I'll end with some discussion and future directions that would be interesting to go in. So first, the ADS-CFT correspondence, pretty much preaching to the choir here, but since its inception, it's given us a very powerful toolkit for looking at problems that were previously extremely difficult to look at, such as non-perturbative string dynamics or strongly coupled field theories. Although we've learned a lot about the correspondence over the years and expanded the dictionary a lot, we still have a lot to learn about it. So it's nice to calculate some simple observables in this setup and see what it gives us, how it behaves in different setups. One of the most simple observables we can observe is the 2-point correlation function. The standard dictionary for calculating these correlators is the GKPW dictionary. We just look at the bulk field about the classical saddle point and impose boundary conditions. The boundary value of a bulk field will act as sources on the boundary, and the CFT generating functional and the gravitational partition function are equated by the correspondence, and then all we need to do is just take successive derivatives of the on-shell action with respect to the sources. And in most cases, that'll just give us some classical wave equation, unless we're looking at fluctuations about the saddle, which we won't be doing today.
In equation 2, there is no time order. Why?
We're going to look at this in Euclidean signature, so we don't have to worry about time ordering.
No. No time.
No time ordering, because this is all in Euclidean.
Time does not exist.
No, there is a time coordinate, but in Euclidean, I don't think you need to worry about the time.
The close time. Then you can encounter some CTC. Close time like curve.
I don't
in Euclidean space.
I don't
if
think
you consider Euclidean time, then you can encounter some closed time like curve. Yeah.
Let's see. We didn't run into issues of that type when we did this, and it's not something that we considered. So I'm not sure if I have a great answer for that.
To my understanding, if we have some periodicity or close time like curve Euclidean, then that just means the temperature.
Right.
When imposing the periodicity, it
right,
behaves like temperature. But in this case, there is no such a kind of concept.
No.
Yeah.
I would say no. Yeah. Right. So the original correspondence was written down for pure ADS and vacuum CFT, but we would like to expand the dictionary. So we want to look at beyond just pure ADS setups. And lots of tractable models have been studied in the past 20 or so years, such as black holes that are in the bulk or dual-thermal CFTs on the boundary. There have been cases where people did some microstate counting using the boundary CFT, or we could look at some extended objects such as string world sheets that end on Wilson lines on the gauge theory. But in particular, today I want to look at defects in the context of holography. When we calculate observables in the presence of a defect, it lets us look at very interesting physics while still being tractable because it'll still respect some reduced symmetry. There's two main approaches when we want to put in defects into holography. We can either put in a background field interaction and then it's a smooth turn on for the deformation and we get a smooth parameter space, or we can insert an extended object like a singular brain. Karsh-Randall model is an example of such a setup. You have ADS5 and you insert this ADS4 brain. But the issue there is we would have a singular brain source in the bulk, so there's a discontinuity in the bulk. But the Janus solution, which my advisor wrote down with collaborators, Professor Buck might be here today on Zoom, but the original Janus solution was a supergravity solution that's dual to an interface CFT that was formed by putting in a dilatonic deformation into ADS5. And that dilatonic deformation reaches two different values at two different asymptotic boundaries, and they meet at an interface, a codimension 1 interface. And this boundary CFT, because of the presence of this interface, respects this reduced conformal symmetry. It looks like this in the 2D language where I12 is an interface operator. And since its inception, there have been several constructions like H-Sugra solutions in several dimensions and half BPS solutions in both type 2B and M theory. Today, I'm just going to look at Einstein gravity coupled to this dilaton in 3D in Euclidean signature, which is a very simple construction, but we can still look at lots of interesting things there.
So could you remind me what is the boundary look like?
What does the boundary look like? Oh, I'll show you a diagram in a second.
Pre-scalar field, no mass term,
Yeah, it's a massless.
massless.
Yeah, it's a massless. It's a dilaton. Okay, so just to make this clear, this scalar field we put in the background is massless, and that'll change our metric in a non-trivial way. But later, I'm going to put in a different scalar field that'll have some very small mass, and that we're going to treat perturbatively. So those are two different things. So, right. So we vary our action, we look at the equations of motion. When we look at this specific solution, it's a Poincare upper half plane slicing. We made this educated choice because we know it'll give us the Poincare equation later, which is solvable. So if we look here, this metric, when we have Cj equal to 0, is symmetric about y equals a half. And then this is the dilaton value, and the dilaton value will jump this much across the defect. When we have a trivial defect, of course, there is no jump in the dilaton. When we reach extremal values for this Cj, plus or minus 1, then the space-time becomes singular. But for the purposes of our talk, we're going to keep Cj very small.
So the radial coordinate is z here, the
Yeah.
radius radial.
Yeah, radial coordinate is z, and the angular coordinate is y.
So if z equals 0 means that point just or
This point, so this is where the interface is. These are the two asymptotic boundaries, and they meet at this interface equals 0.
So infinity boundary is at that line.
Yes, this is the boundary in the Poincare slicing metric.
But it's a similar question. So z equal to 0 covers the whole line or only the point?
Just this point. Z is the radial coordinate, and y is the angular coordinate.
And z equal to 0 is the boundary.
Yeah, so there's three boundaries, this equals 0, in here, and y equals 0 and y equals 1 boundaries. And this is the structure of the boundaries.
Let's just concentrate since I do not forgot everything. So let's say take a c equal to 0, cj equal to 0. Then what is the geometry?
Then it's going to be symmetric about this point, and the defect is trivial, so we won't have a jump in the dilaton.
Okay, and the metric is just, is it ADS metric?
Yeah, so this is an ADS3 version of the Janus solution. When CJ is 0, it's just pure ADS. When we turn on this deformation parameter, it becomes what's called the Janus solution, and it has this kind of structure where there's this left is what I'm going to call it, left asymptotic boundary at y = 0, right asymptotic boundary. They meet here, and the dilaton takes on different values. That depends on this deformation parameter.
What is CJ?
It's our deformation parameter. It's just a parameter that we dial to keep deforming the.
Actually, integration constant from equation motion?
Hmm?
Integration
Oh yeah, it's a
So
integration.
it looks like a
constant.
mass, black hole mass.
Black hole mass.
Where is the mass parameter?
The mass parameter.
Yeah.
I'll actually relate all the parameters later in the slides. The mass and the
The
conformal
geometry is
dimension.
not black hole, okay?
No black hole.
No black hole.
No black hole.
What is the CJ?
CJ,
Please characterize something.
it's a parameter that we're keeping small. And this we just get from solving the
Which
equation.
comes from integration constant.
Yes.
And it looks like a black hole mass.
Mm-hmm.
Conserved constant.
Mm-hmm.
So I'm wondering what is the origin of CJ?
It's related to the mass, but I haven't thought about it in a black hole angle because we don't have a black hole.
Is there any horizon or not? Horizon?
No.
No?
No, it's just the bulk is non-singular and the discontinuity is just on the boundary.
CJ is not, something, has nothing to do with the black hole mass. Then what is
It has to do with the dilaton is massless. It'll be I think I can answer your question later. I think it'll become more clear when I show you the equation of motion that we get later when we put in the probe scalar. So I think it'll become clear. Yeah.
So if you turn off CJ,
Mm-hmm.
the metric is not just trivial Poincare metric. It's not written like that. It's more complicated. Even if you turn off C,
Mm-hmm.
the typical Poincare metric was z square plus d tau square plus dy square over the c square. But now you have some weird 1 over y, 1 minus y factors.
Mm-hmm.
So I feel like z is not the typical radial coordinate in Poincare metric, right?
So this isn't exactly the conventional Poincare metric. It's we take a Poincare slicing of this non-pure ADS setup. We've deformed the space-time, so it's different now.
So what I mean, my question is, if you turn off CJ,
Turn it off.
turn off,
Mhm.
CJ is, let's say it's 0,
Mm-hmm.
then the metric is just not, at least not apparently Poincare metric, right? So, but is it still equivalent to Poincare metric under some coordinate transformation? Or
It should be.
should be.
Yeah, it should be, because then it's just pure ADS.
Nice.
Mm-hmm.
for constant y? For constant y, you can write this metric.
No, I think you're
But when
saying
we-
for
Arbitrary
0C,
Yeah, when we
it's a
turn.
three-dimensional Poincare metric.
Mm-hmm. So this looks a little weird because we wanted to milk out a specific equation of a specific form, but when CJ is 0, we should be able to do some mapping to make it look just like the regular Poincare, because it is just pure ADS in that case.
Y direction is torus or interval?
It's an interval from 0 to 1.
Interval.
Yeah. Any other questions?
So maybe by some simple coordinate redefinition, can you put that metric for CJ equal to 0 easily into the usual ADS metric?
It should be, yeah. Yeah, this is a very unconventional, kind of wonky looking form. But we chose this because that makes the probe scalar equation of motion a lot easier to solve. So it looks a little weird, but when CJ is 0, it is just pure ADS.
Locally same, but globally different. It would be different. CJ equal When transforming coordinate transformation, if you can eliminate CJ, then locally equivalent, but globally inequivalent.
So this is the Janus solution, right? And how should I visualize in terms of metric? If I just go from y equal to 0 along the up to y equal to 1, so maybe at the y equal to 0, I am starting from some typical ADS metric, then it is a deformed or something.
So this is the boundary, this is the bulk. And the boundary has a funny structure where it's two separate boundaries joined here with some discontinuous dilaton value. So this is the ADS boundary, this is the
Yeah,
ADS
the
bulk.
question is, if CJ equal to 0, along there is no y dependence in the metric essentially. Can I say that? So it's not Janus, it's just only one phase of Z, right? But CJ makes some two-phase or multi-phase kind of structure. How should I visualize that kind of method? So by putting CJ, what is changing? So just I can easily visualize the metric.
So I think maybe I misunderstood. I think the logic is starting from the typical easiest Poincare metric for ADS 3.
For CJ equal to 0, that's it.
Yeah, even before thinking about this metric, just consider Poincare metric, it's ADS 3. Now, in that coordinate system, the boundary has to be just C equals 0. But that's the typical boundary. Now you do very weird coordinate transformation so that the boundary is now in this new weird coordinate system, it's not just Z equals 0. It consists of Z equals 0 and Y equals 0 and Y equals 1. So it's very weird coordinate system. So boundary is now described not just by Z equals 0, but that line is the boundary.
Well, Z equal to 0 is a kind of in the usual R coordinate sense, it's an infinity point.
Yeah.
Infinity point should be essentially described by some kind of angle coordinates.
Yeah,
So I thought
think-
y is one of the angle, tau is the other angle, what time?
But if for generic value of y between 0 and 1, it's not boundary. So in this weird coordinate system, boundary consists of y equals 0, y equals 1, and in the middle, which is equal 0, is also boundary. I think
For the coordinates, we have y, z, tau.
yeah.
So tau is clear, Euclidean time, right?
So I'm not sure about that yet because I didn't derive any coordinate
Right.
transformation.
So to me, it seems that tau is a Euclidean time. Is that right? Not necessarily yet.
Yeah.
Is it Euclidean time or not?
It's hard to tell because even if you turn up C equals 0, there's an overall factor 1 over y, 1 minus y, which is not in typical Poincare coordinates.
That is right. So maybe that my question was whether that can be absorbed by some rescaling
Yeah,
or some.
I think coordinate transformation should be very non-trivial between typical Poincare and this. So in this coordinate system, I think the whole point is boundary is this line, right?
Yeah.
And then
But
yeah.
putting aside the tau, so in the ocean, since it is a three-dimensional geometry, boundary is a two-dimension. Yeah.
Yeah.
And so two-dimension should be described by y and tau. Tau is trivially some circular structure, seems to be.
So
And the y seems to be kind of it's an interval, but it's a kind of angle.
I think the boundary for now is described by first tau, because tau is not restricted, and also non-zero z.
Yeah, so
The boundary is described like that, right?
the boundary is described by Z and tau.
Z and tau, but the boundaries at the z equal to 0. That's the boundary, no?
This is one of the boundaries. Yeah.
That's the part, yeah.
If C were 0, that's the only boundary. Is that right?
Oh, now I don't think so. If c is 0, boundary is still that, right? Y equals 0, y equals
Yeah.
1, and z equals 0.
So the boundary is parameterized by Z and tau, and they when C is non-trivial, there's two separate boundaries, y equals 0, y equals 1, that's joined here. When the defect is trivial, they are one boundary, but it's hard to see that from this metric form because it is so non-conventional.
Okay.
Boundary is a straight line. Yeah. Boundary.
So that is the three-dimensional Janus solution. So now that we have this background, we're going to add operators to it by adding fields to the bulk action. What we're going to add is just a probe scalar field. And on the boundary, that's dual to a scalar primary with this scaling dimension. This is the action for the probe scalar. So we are keeping the mass small, but it can be negative as long as it's above the Brighton-Lohner-Friedman bound. And in this case, we take the standard quantization, which means taking the conformal dimension of the operator to be delta plus. You could take it to be delta minus because both delta plus and delta minus are normalizable in this case, but we won't worry about that alternate quantization because this is more convenient for our purposes. And we are not going to back react anything, and we are not going to look at higher point interactions because we're looking at the classical saddle point and the bulk, which is large N. So any corrections to the 2-point function will die off very fast.
Mass square is negatively bounded. Why? N square is.
Oh, I'm saying it could be this value in that case. So when the mass is positive, the delta plus is the normalizable and the delta minus is the non-normalizable node. When it's this value, they're both normalizable. So we can pick between delta plus and delta minus for the conformal dimension. Then we're making this choice.
So over here, it is implicitly assumed that the Z goes to zero limit. I'm sorry. Confused.
Oh, are you looking at this? So I'll explain this right now. So we're going to take the holographic renormalization. When we evaluate this on shell, this is the boundary term that we get left. There are divergent pieces that are exactly canceled out by this counter term. And we put in this slight deformation here because the delta minus will diverge at the boundary if the mass is positive. And then we take epsilon to 0.
Okay, so I see. So
This
S
is the
probe
cutoff.
lives in the probe lives in the bulk, which is 3-dimensional.
And then when you match it to the boundary value, that is the source that I talked about when I.
So I thought I see boundary is described by Z and the tau. What is the Y value at the time? So Y is either I see 0 or 1.
And those are the two boundaries. And then we're regulating it with the cutoff because the delta minus mode would diverge.
What is the reason that diagonals survive?
Oh, well, because if you look at a field and like drag it to the boundary, it goes as like Z to the delta plus and then like Z to the delta minus with some value, and delta minus, if you look here, oh well, not Z here, Y here, when it's delta minus.
What is the physical reason why the
Physical reason why it diverges? Well, because the delta minus modes in that case supply the source. So if you're at the source, it should diverge. So for positive mass, delta minus is the source, and the delta plus sets your 1-point function normalization. And then this is just to account for the negative mass cases, which is possible.
this seems to be a UV divergence, right? So
Right.
if you approach the actually boundary,
Mhm.
approach the boundary, actually, the characteristic feature of AD3 is actually potentially divergent at the boundary. So I think the reason why the action 7 will be divergent is actually due to the infinite potential of AD's boundary. Intuitively, I think. Additionally, actually, where is the rescaling of metric? Rescaling of metric.
Rescaling of the metric?
Yeah. common, yeah, you normally use the actually bulk metric. But to my understanding, actually, we need to introduce the scaled metric at boundary. Why scaled metric?
Ah, I see, because it's not conformally flat, is that what
Yeah,
you're talking about? We kept it in this slicing and we didn't rescale it. We just kept in mind what factors would be added or missing because of the non-conformal flatness. I can point that out later, but
Okay.
it's just an overall
Not
factor that
flat.
Right, so this probe scalar, we can decompose in terms of the Poincare upper half plane eigenfunctions. We take this factorization ansatz, and then the H2 eigenfunctions have this form, and then our scalar field we can write like this. We throw that back into our equation of motion, separate the variables, and then after this rescaling of the radial piece, the equation of motion takes on exactly this form, which is what we wanted. This is called the normal form of Heun's equation. Heun's equation is basically a very natural generalization of the hypergeometric function. It's a second order ODE with 4 punctures instead of 3. So it has lots of similar characteristics. The only new feature is this accessory parameter. And we see that the spectral parameter for the H2 eigenfunctions only enters through this accessory parameter.
What is G? GSK.
This is the basis for the H2 Laplacian.
So scalar component? G. What is the origin of G?
Oh, it's a part of the scalar field. So we factorize the, yeah, this is our probe scalar, right? And then we factorize it like that so that we can just worry about the radial part. The radial equation of motion after this rescaling gives us this nice form. And yeah, I've written down how the parameters of Heun's equation relate to the parameters of our problem here. So now what we want to do is we want to solve this differential equation.
So if Cj goes to zero limit, how does the Heun equation?
It should become the hypergeometric. So we have this equation of motion, and now we want to look at the 2-point function because we want to do some interesting things with it later. And again, by the GKPW dictionary, this bulk scalar field, when you drag it to the boundary, can be matched to sources on the boundary. So we write it like so. This J is the boundary value, which acts as the source. This is the bulk boundary propagator, which takes on this form. And we just picked the normalizations to be this way because we rescaled the scalar field and all that. And the nice thing about the normal form of Heun's equation is there's no first derivative term. So when we calculate the Wronskian, so take the y derivative of this, that's going to be 0. It's constant, so we can just calculate the Wronskian at the boundary value and just take that. And this will be our bulk-to-bulk propagator by the Wronskian formalism. And then, if we want to look at 2-point correlators by the GKPW dictionary that I mentioned earlier, we just take successive derivatives of the normalized action.
The previous one, the left and right, the correlation functions, they are becoming the same when Cj goes to 0. The
This
bulk boundary operator. Bulk boundary correction property.
They become the same when Cj is trivial. Right.
Seems to be then okay. Good.
Right, so we again want to calculate the 2-point functions because we want to look at how this defect at z equals 0 affects our observables. We insert sources on the same side of the boundary versus across the the defect, and we're going to look at how they behave as we bring the sources close to the boundary. So that is what we're after. And because we have this equation of motion, we are going to need to get the connection coefficients to solve for these 2-point correlation functions.
So essentially, you have some analytical form of the bulk boundary operator, the propagators. That's it. Just one thing. I see. So the G in the green function is a usual green function or bulk
Yeah,
relation.
bulk propagator.
Okay.
Okay, so we want to solve this equation, which is very difficult to do analytically. So I'm going to take a little detour to tell you how we did that. So again, Heun's equation is a second order fusion ODE, the generalization of the hypergeometric equation. The nice thing about this equation is it pops up in several different places. There's the HT correspondence that relates the Nekrasov instant on partition function in a D equals 4 n equals 2 SCFT to conformal blocks in the Liouville 2 DCFT. And it also shows up in this setup, which might be more familiar to the audience. If you look at thermal correlators in ADS5 CFT4, look at the analytical structure of that, we can read off the quasi-normal mode data. But
The boundary you are considering is non-flat. So where is the
non-conformally flat.
boundary metric in the correlation function? In the previous page, you derive the correlation function. So it seems like its definition, correlation function can be defined in the flat space. So I'm wondering, you didn't rescale the metric. You just use the bulk metric at the boundary. It's insufficient to define the boundary. Actually, after while rescaling, you can reach the real boundary. Then you can get the flat boundary space. And then you can calculate the correlation function. So I'm wondering why you did not actually perform the rescaling of metric.
Right, we didn't do that because it's just an overall factor that makes itself very apparent at the end.
Yeah,
So-
factor.
Yeah,
Anyway, so and after rescaling, you mean that actually you can get the flat metric? Flat metric? Do you mean that actually your metric at the boundary is a flat metric?
I think it's conformal.
conformally flat if you rescale it, but
After rescaling,
but it doesn't cause a problem when we calculate the correlator, because again, it's very easy to see where that not conformally flat behavior went.
you will not consider stress tensor on the boundary.
Hmm?
You will not consider stress
That's
tensor
not what
on
we
the
do
boundary.
for this.
Okay.
We will not do that for this.
Okay.
Conformally flat is the left boundary and the right boundary is separate. Is that right? The whole boundary is conformally flat.
I think it should look the same because that overall factor you get doesn't depend on whether it's the left or right boundary. It's just like 1/z, z prime delta, like to the delta plus.
As independent of y coordinate.
Yeah. It just depends on the z coordinate. So I think it should be the same. Okay. So back to this. So what we're going to do is we're going to take advantage of this AGT correspondence and also the fact that it's a 2D CFT on one side of the correspondence. So we can get all the data that we need from this data. We can look at degenerate blocks to get the exact same differential equation and then read the data off from there. So this is a slight detour, but you'll see what it's for at the end. So just to catch everyone up, just quick CFT2 basics. Of course, we have our infinite dimensional symmetry algebra, the Virasoro algebra, primary states annihilated by this set of generators, descendants obtained by this set of generators applied to the primary. We have null states, that means descendant state that's also primary. The nice thing is that if you have a null state, they're orthogonal to every state in the Hilbert
The
space.
absolute generator has been defined on the boundary throughout the actually Fourier mode of stress tensor. All right. So ln commutation relation, in other words, actually PT algebra, stress green function of two stress tensor, PT, expectation value. Then you can calculate the ln commutation relation. So it means you already consider stress tensor. Actually, ln is just a component of stress tensor.
So this
Stress tensor?
CFT is completely different from our holographic CFT. This is not holographic. This physically has nothing to do with our setup. We're just borrowing this, what will be a Liouville CFT, because it gives us the differential equation that we want. So this is not our physical setup.
Yeah, anyway, equation 19 was defined on the flat boundary.
So yeah, this is not the dual holographic CFT2 that we have. This is entirely separate.
ln is not a generator of diffeomorphism. Okay.
So this you'll kind of need to physically detach it from our setup. It's a completely different CFT2. It just happens to give us the equation that we want, so we can use the complete data there to give us the 2-point correlation.
Boundary CFT is a local or global? I mean, symmetry can be classified to local or global. So diffeomorphism is a local. So I'm wondering, what is the definition of ln? What is the geometry of the boundary? So ln is a generator of CFT. So what is the group of CFT? Local?
She said it's not physical.
Yeah, this is a different CFT2. This is not holographic.
Anyway, CFT2.
Yeah.
Yeah, so this is. I think
CFT2, that is not our CFT2. Okay, let me drop something. So the setup that we have is Janus equals 3 dual to holographic CFT2.
Right.
This is what we're trying to solve. We're separating ourselves from this for a moment to look at a Liouville CFT2, which fundamentally isn't holographic, right? It doesn't have smart flowing modes.
Conformal symmetry is a local or global?
For this guy?
Yeah.
Oh, that's what you
Or
want.
CFT2. Yeah, over there. CFT2.
This?
Yeah.
Um,
My question is local symmetry, or whether the CFT is related to a local or non-local.
I don't have a good answer for that because that is not the angle we looked at it in.
Maybe that CFT2 may live on the thousand space. And I think I forgot, but according to the Brownell holographic renormalization, even for the pure gravity system, there is some well-defined energy momentum tensor according to the Brownell, and people have done such thing until 1990s. I guess it's more or less well understood. So from that energy momentum tensor, in principle, this can be derived like this.
So local
But
or
anyway, it's a local.
then it means the central charge should be 0.
No.
You mean local symmetry, then there's no central charge. Central
Right.
charge cannot be allowed in the local symmetry.
The central charge is not 0 for our setup.
Yeah, in this
But
case,
it doesn't
I think
jump
C is
into
not
that.
0. So in that sense, actually, lower space.
I see.
Yeah. Yeah.
So the
As for local
think-
symmetry, central charge is always 0.
I see.
Yeah.
Anywho, so this is our physical setup. This is separate, and then Liouville CFT related to Vapor conformal field theory. to get the data for this. So these two are physically
The
separate.
boundary is flat. So in this sense, it is flat CFT.
Right. Okay, so back to this. Null states are orthogonal, so when we calculate correlation functions involving null states, they're going to give us 0. Once we apply the local word identities, that'll give us the differential equation that we want. Okay, I wrote down the legal action here for completeness, but we won't need this at all. We're just taking a bootstrap approach. The central charge here is parameterized by the background charge, and the background charge is related to the coupling in this way. Primary operators have this conformal weight, and we want to look at null states, so we're looking for degenerate Verma modules. They occur for this discrete set of momenta parameterized by two integers, r and s. And to get the quantity that we want using this correspondence, we're going to start with the 4-point function, and then we're later going to insert a degenerate operator. But when we have this 4-point function and insert OPEs between different channels, we get the S, T, and U channels. We are going to take the S channel because it's the simplest.
Here C is actually 1 plus 6q squared, which is non-vanishing. But the gravity coupled actually in the action. So why? Central charge is not vanishing, even in spite of TQ with invariant action. Why? Total central charge should be always 0. But here actually C is non-zero. Yeah. Q equals 0, actually C is actually 1. So it means actually conformal weight is 1. So I'm wondering why C is non-vanishing here. Because the gravity coupled, no longer flat space. In flat space, central charge, non-vanishing central charge can be allowed. But in gravity theory, total central charge has to be 0. So it has to be 0 always to keep the deformity. So here actually C is not 0. So what is the meaning of central charge C here?
Well, it's just it's not non-gravitational, it's just a separate.
Which are,
Oh, this R?
yeah.
Um,
Then how to calculate the central charge C here? Stress tensor, TT algebra, or so?
I don't have a great answer because we never really used this action. I just put it in there in case people wonder what it would look like. But again, we never actually put the action to use, right?
So this file is quite different from the 5 field you introduced in the video.
Oh, yeah, this is completely, so this is completely different. We've taken a detour, but we'll come back to our physical setup.
Yeah, anyway, Weber theory is also, I think, conformal field theory. Because the action is conformally invariant. So in this case, conformal transformation is a local. So I'm wondering why the central charge is not vanishing. How to get the central charge C here? Commonly TT algebras from the green function of TT product or LN, whatever. Okay. I think total central charge should be 0. So C here, I think partial central charge for psi. Yeah, if you quantize the total system, you have to introduce the ghost. I think you missed the ghost contribution. So if you encounter ghost contribution 2, then you can get the vanishing total central charge, I think. I don't know the right answer in my conjecture.
Okay.
Yeah,
Back to the topic at hand. So we take the S channel OPE to get those conformal blocks. And the formula are available in this recently published paper. And the T-channel formulae were more conventional, but this tends to be more tractable. And then from this 4-point block, we're going to insert a degenerate primary here to, in the end, get the differential equation that we want. The intermediate momenta we get from the degenerate primary fusion rules. And these are the two two blocks that we're going to look at. And respectively taking the y=0 OPE limit here and the y=1 OPE limit here, the conformal blocks take this form. So these factors that pop out here are later going to become the leading exponential behavior for the Frobenius solution. And then this is what's left over. And because we've put in a degenerate operator, they're going to obey the VPZ decoupling equation. We get that by looking at, well, we've inserted V2, 1. So there's a null descendant at level 2. So it's going to obey this equation. So we're going to apply this combination of generators to our conformal block, and then use the local word identities to turn them into differential operators. And this is the equation we get with the operator taking
Could you
this form.
remind me what was F, curly F?
It's this part after you've inserted the OPE between these two.
So there is some background metric dependence, so that's why it is different from, there is a Y dependence.
The Y here is oh yeah, the Y is the coordinate in this CFT. And then this T here is where we put in this degenerate operator. Okay. So we have this conformal block that obeys this differential equation, and the solutions near the y=0 and y=1 punctures are related by this transformation matrix, which involves solving some complicated Clebsch-Gordon procedure, but it's taken from that paper. But for our purposes, we can just take this result and that'll give us the connection coefficients. So we are going to take the semi-classical limit in this Liouville CFT, and that corresponds to large central charge, the coupling constant going to 0, and the momenta are going to diverge, but this ratio will be finite, and we'll call it theta and sigma for the intermediate momentum. And in this limit, lots of nice simplifications happen. The conformal weights of each operator factorize in this form, and this factor and this factor are later going to be the leading exponential factors for the Frobenius solution. And we also get a factorization between the heavy parts and the light degenerate operator insertion. And the heavy block will exponentiate in this form. And what we get is this normalization factor, which I'll make explicit in a second. And this light block is going to be identified with the solution to Heun's equation. And this hangs around. And what we're going to do is we're going to take this limit and collect terms order by order.
C equal infinity means the semi-classical limit. Why? What do you mean the semi-classical limit? Taking C to infinity. Why? Semi-classical.
Why is it semi-classical?
Yes, semi-classical limit means the limit in the gravity or in the CFT side.
This is, let mean, this is what's called the semi-classical limit in the Liouville CFT theory. Why? I mean, I'm not sure if looking at this in like a gravity angle makes sense because it's definitely not holographic. Yeah.
Actually, in front of C, actually H bar appeared. And so C goes to infinity means actually quantum correction is very, very big. So why are you calling this the semi-classical limit C goes to infinity?
I'm not sure if I could tell you why. It's what it's,
C goes to infinity.
yeah. It's what it's called in the literature, but I never looked into why is it the semi-classical limit.
Yeah, I think about that. Yeah.
Okay, so we take this limit and when we collect terms that are at this order in terms of B, it takes on the normal form of Heun's equation. This normalization factor comes from the fusion of the light degenerate operator with the heavy operators. And like I said, the light block becomes identified with solutions to Heun's equation, and they're going to be related by this connection formula, which we know previously from the fusion transformation matrix, and now we have this normalization coming along from the ride, for the ride, and this epsilon and epsilon prime previously was parametrizing the two Liouville momenta that we got from the fusion rules, but now they label the two independent, linearly independent Frobenius solutions at y equals 0, no, not oh yeah, near y equals 0 and near y equals 1. And then to fix the semi-classical Virasoro blocks, we go to the SCFT side of the AGT correspondence, and from instanton counting, the large T expansion, the coefficients get fixed like so. In principle, we could go higher order, but we stopped at second order because that was sufficient to get the first non-trivial correction to the quantities that we want. And then this semi-classical block is related to the accessory parameter by the Zamologic relation. And then what we're going to do is we take the large T expansion for the intermediate Liouville momentum as well, plug that back in here, solve that order by order. And that's going to supply the data we need to solve for the 2-point function. So that was our little detour, just so we can get the mathematics that we need for our physical setup. Back to our physical setup, we have our probe scalar equation of motion in the 3-dimensional Janus solution, and looking at how T, which is what the light degenerate operator insertion depended on. It depends on our Janus deformation parameter in this way. So the large T expansion is a small CJ expansion. The dilaton, since it's massless, is dual to a marginal operator on the boundary, so it doesn't trigger an RG flow. And this small CJ deformation, the Janus deformation, can be thought of as a CFT perturbation problem. And the intermediate Liouville momentum, which we expanded in T earlier, we can reparameterize it as a small CJ expansion, and this is the form that we get after organizing everything. Questions so far? Okay. So there are two linearly independent solutions at y equals 0, y equals 1, which are our two left and right ADS boundaries, and the normalizable solutions are the y delta plus 1 minus y delta plus. So I'm going to pick those, and I know how they behave near the boundary. And each normalizable solution, I also want to look at how it behaves on the opposite boundary. That is where this EGT correspondence comes in. The connection coefficients tell us how that solution behaves on the other boundary, and we can fill that data in from the detour that we took earlier.
And here, so where is the CJ dependence of here?
It's hiding in the connection coefficients.
Here.
Right, so because the intermediate Liouville momentum here has a CJ expansion, and if we look at the connection coefficients, the intermediate Liouville momentum is hiding here, right? So when we get the 2-point function, we want to look at the argument of this gamma function, and that's going to supply the poles. So that's where the CJ comes in through this parameter sigma. Yeah. Okay. Like this, and again, our bulk boundary propagators using the Brownskian method are of this form. And then when we want to look at the 2-point correlators, they just come out to ratios of the connection coefficients and then integrated over the parameters of the H2 eigenfunctions. So this is the form we have. We have the connection coefficients from the HET correspondence data. Now we just need to throw everything in and solve it. So it was quite the detour, but it's analytical and it's exact before we do the perturbation. So that is why we did that. So after we put in the parameters of our problem, it takes this form. As expected, the right and left correlators look very similar, and they match exactly when the defect is trivial, because then this factor just goes away, it becomes 1. When the deformation is turned on, everything else is the same except for this normalization factor. When we have the defect on the sources on the opposite sides of the defect, it looks quite different. But what we need to pay attention is this gamma function here. Oh, and I should make the notation clear. This plus minus means gamma, this plus sigma times gamma, this minus sigma. So that's what that means. It's just a shorthand to make sure it's not everything's overcrowded. And as a sanity check with this result, we calculated the correlation function for the trivial defect, which is the pure ADS case. The S integral we can just evaluate by looking up the integration table, and it gives us the standard form of a conformal primary with conformal weight delta plus. But again, this factor hangs around because we were not in a conformally flat frame.
CJ is 0. It means the
It's pure
space-time
ADS.
is pure.
Mhm.
What is the definition of pure ADS? Globally ADS3 or ADS2? Or pure ADS? Global ADS? Pure means pure.
Pure means it's
Commonly 1 plus R square type.
Mhm.
There's an alternative form is just without 1 R square. So which one is pure ADS? Global ADS or
I'm not sure I understand the question.
so how to write the pure ADS3 in terms of metric?
Oh,
If you
the
write the metric for pure ADS3,
Mhm.
how to write the pure ADS?
Oh, it would.
One plus
I guess you could write it in global coordinates, but I think writing it in Poincare coordinates would be
Poincare coordinates.
easier because that's the slicing choice that we made. We took the ADS2 slicing.
Starting from the Poincare coordinate, you can get some metric. Then it means actually commonly normal form is 1 plus R square type
Mhm.
in terms of radial coordinate.
Mhm.
So it means without drop the 1. You mean pure means 1 without 1.
Yes.
I think so, yeah.
Oh.
Yeah, so in that sense, CJ is non-zero case. It corresponds to actually molecular geometry.
Why does non-zero seem like that?
Because CJ equals 0 means actually it corresponds to M equals 0. So M equals -1 case is global ADS3. And M equals 0 is pure. You mentioned pure. So CJ is non-zero. So for instance, positive, CJ is positive.
Yes.
then CJ, I think the CJ should be actually reference.
Mm.
Yeah, you mentioned actually that is actually integration constant. Integration constant should be physical quantity. Yeah, so it should be a reference.
Yeah, and I mean, I'm not sure if that interpretation makes sense because physically we don't have a black hole. I think you should think of that integration constant as related to that dilaton that we're using to deform the background.
Yeah, dilaton also deformed. Yeah. But the CJ was appear in the battery. So there is some horizon. CJ is not. Yeah, CJ is positive definite. Okay. So that is a smoking gun. Additionally, you mentioned actually that is actually integration constant. Integration constant should be identified with the physical quantity.
In our case, it's the dilaton jump. But
Dilaton jump, the physical quantity. From the point of physical quantity, actually CJ should be a mass or anyway charge. It should be a charge. Anyway.
Right. So we did this case as a sanity check. We have the expected form when the sources are across the boundary. It's very similar to just the conformal primary form. We just reflect Z prime and minus C prime to get the same thing.
So if mass of the scalars is 0, then delta plus and delta minus is equal.
No.
No.
What was the delta?
Plus and delta minus, we have to go up for that. It's one, oh, there it is. It's this. So even if it's 0, they're different.
0, that's okay, good.
All green function could vanish.
Whoops. We were here. Okay, so that's the trivial case, but now we want to look at the non-trivial defect. In that case, the S integral isn't readily computable, so it's a little trickier, but we can read off the data that we want with some foresight. So there's this thing called the boundary operator product expansion. If you take a bulk operator and drag it really close to a boundary, you can expand it in terms of the boundary operators because it becomes indistinguishable from the excitations on that boundary. So it'll look like this. This factor just comes from the conformal symmetry. And if you solve the differential equation that you get from applying the Casimir of the reduced conformal symmetry that our interface respects, the OPE takes this form. And I'm going to define two different parameters, this cross ratio for the left, and right correlators, and this cross ratio with the plus here instead of minus for the left, and right, left correlators. And when we take this psi goes to 0 limit, it just looks like a standard bulk OPE. But if we take, and it's not possible for the left, left case because there's the defect sitting in between the sources. And then the psi and psi tilde goes to infinity limit. It corresponds to keeping the sources separate and just keep taking it close to the interface here. And that's what's going to take this boundary OPE form. So we are going to look at this limit because that'll tell us the data that we want about the spectrum of the boundary operators. So instead of evaluating the S integral, which isn't readily computable, we integrate out the K by doing a Fourier transform and taking some transformation rules for hypergeometric functions. And this is the form we get. At first sight, it looks a little unwieldy, but if we compare it to here, well, there is our 2f1 hypergeometric function, and this factor and the coefficients here So that tells us, well, for this S integral, which we couldn't explicitly compute, if we find where the poles sit for this integrand, the residues will be the boundary OPE coefficients, and the locations of the poles will be the conformal dimension of the boundary operators. So we are going to do that.
Did you use the mathematical
For
integration with respect to ds?
for this.
Oh.
So so to calculate the residue, we plugged it into Mathematica, but to get the pole locations, we just need the form of sigma, right? Because it's just this gamma that supplies the pole, which we already got earlier. Well, that also we used Mathematica, but yeah. Cool, so we are ready to read off the boundary operator ceiling dimensions, which are again going to be locations of the poles.
I understand the logic. So logic is that the boundary 2-point correlation function calculation. You start from some bulk to boundary or something like that, taking the limit. That's the way you got.
Right, so we got the bulk boundary propagator, and then we take the limit to the boundary, and that's the GKPW dictionary, right?
Take the limit of the bulk going to the boundary.
So the boundary, the bulk scalar field, the value of that field on the boundary is the source, the J.
And then the thing is that it's not operator product standard, but when the bulk operator approaching to the boundary, so writing that in terms of the local, in terms of the operators at the boundary. So is it straightforward?
Which part is straightforward? You mean
Previous pages you.
the sixth page?
There. Yeah, first equation.
So yeah, this deducing that it's in this form is a whole process, but this is known in the literature. So what we're doing is, well, this is known, and that's just from using the reduced conformal symmetry.
Is known what the B coefficient is and what the O hat operators coming in the extension.
We
Those
are
are well known.
we are going to find that. That is the result of our paper. We found the B's and we found the O hats. Yes. So we look at the locations of the poles. The S runs along the real line, so we can close it on the upper or lower half plane, but we are restricted to closing it on the lower half plane to preserve unitarity. So of the two gammas, the plus and minus sigma, the minus sigma gamma function supplies the simple poles. And when we turn on the Janus deformation parameter, it just shifts the poles up slightly, like so. And this shifted pole location, after throwing it into Mathematica, came out to this. And this is one of the main results of our paper. We got the spectrum of the boundary operators in terms of the Janus deformation parameter from using the data of the AGT correspondence. So this is the first main result, and there was no first order correction in CJ. Cool, so that is the spectrum of the operators, and we can also read off the OPE coefficients once we calculate the residues. It comes out to this. And again, for the left, and right, the only difference is in the normalization factor, which we'll trivialize if we turn off the defect. And they should satisfy consistency conditions. Left, left times right coefficient should give this squared, which it does satisfy. So that's good news. So that is our second main result. So that is about it. And just to summarize what we did, it was quite the trip. We found a new instance of Heun's equation, which is abundant in the literature, but it wasn't found for this D = 3 Janus case. And we got the holographic CFT data from this completely separate non-holographic Liouville CFT. And so throughout this, we just assumed that the difference between the delta plus and delta minus were non-integer. But when they are integers, you do need to be careful about defining the solutions. But the technology with the connection coefficients should remain very similar. We didn't deal with this in our paper, but I found this source to be pretty pedagogical if you want to read about that. And to end with some future directions for this research. So there is a half BPS Janus solution in D equals 3, N equals 8 supergravity. You take a consistent truncation of type 2b, compact it right here, and M4 is either T4 or K3. And this specific Janus model has been studied a lot. People have calculated the TT correlator to look at transmission and reflection coefficients, and people have calculated entanglement entropy. Because this is an explicit solution, we could again calculate the 2-point correlation function like we did here. The scalar fields in this theory live in this coset, so we can use this similar technology to get this correlator, get some nice bounds and inequalities. The special thing about this solution is instead, unlike the solution that we looked at, it's an RG flow interface, so there will be a jump in the central charge of the CFTs on the boundary. And this you can think of as a flow between a UV CFT and an IR CFT on either side of the defect, and the slicing coordinate in the bulk is what creates the flow. Another direction we could go in, which is actually what we're pursuing right now, is looking at spin-2 excitations in a different Janus background. You have a warped ADS4 embedded in a 10-dimensional space, and by separation of variables, you can actually make it look like a massless scalar wave equation in 10 dimensions. And this, interestingly enough, is also of the Heun form exactly. And you can calculate the mass spectrum explicitly from, again, the connection formulae. This paper, they did this part numerically, but we are going to do it analytically this time. So that is about all I had for today. Those are my cats. Thank you.